Good morning, everyone, and thank you for registering for this webinar. This is the second webinar in the series that we have started. It began on 24th March. I am Dr. Veda Sandeep Nagaraja from Tyndall National Institute, Ireland. I am the host for this webinar series, and I have with me today as a speaker, Dr. Sambuddha Khan. After I give introduction about him, he will begin the talk for today. Dr. Sambuddha Khan is working in MEMS domain for past 15 years. He has obtained his PhD in the field of MEMS inertial sensors, particularly in accelerometer from the Indian Institute of Science, Bangalore. After his doctoral thesis, he went on to do his postdoctoral research in University of California, where he worked with the Professor Andre Shekel in the area of silicon-based inertial grade high precision gyroscopes. During both his PhD and postdoctoral research, he was engaged in hands-on fabrication of the devices he was working on and used the MUMPS process quite extensively. He was working in industry for almost 7 years before joining Tyndall National Institute as a senior scientist in the Piezo MUMPs group. His research expertise include MEMS resonators and inertial sensors, microfabrication, packaging, and system integration, testing, characterization, design validation of MEMS devices, etc. I welcome Dr. Sambuddha Khan, and I would request all the participants to leave their questions in the question and answer chat box, which we'll take up after the talk. Now I hand over the stage to Dr. Sambuddha Khan. Please start the session. Thank you.
Thank you, Dr. Veda, and good morning, everyone, and welcome to the second session of Europractice webinar series on MEMS. Today, I'm going to talk on MUMPS technology platforms from MEMSCAP, enabling low-cost prototyping. I am from Tyndall National Institute, and as Dr. Veda said, that I am a senior researcher here, senior scientist. So for those who could not make it during the first session of MEMS webinar, I would like to give a quick recap on what was discussed by Dr. Veda Sandeep Nagaraja. So she introduced you with the concept of MEMS and the application of MEMS. And also she talked about different transduction mechanisms that are used for designing and developing MEMS devices. She also touched upon a few aspects of fabrication and the challenges involved. And she ended her talk with packaging and integration of MEMS devices. Today, I'm going to focus more on fabrication aspect of MEMS devices and how MEMSCAP can be of help to you in order to fabricate the devices that is designed by you. So, via Europractice, there is a program that's called MUMPS, multi-user MEMS process, that users can access via Europractice, and the service MUMPS service is offered by MEMSCAP foundry. So this MUMPS, what is MUMPS? MUMPS is multi-user MEMS processes, and this is a kind of a multi-project-wafer service where many participants can participate in the same run, and their designs can be incorporated on a single mask and co-fabricated along with all the other designs. And but in order to participate in those runs, the user must have to follow a standard guideline or the design rules. So what happens is that if you follow a standard design rules with a highly standardized process, then you can participate. All the designs will be almost the same, like or they will follow the same process, and you will be able to share the same wafer. So anyone in this particular service, anyone can participate, starting from academia to industry. It's very cost effective because the cost is shared between all the participants. The processes are highly standardized, and that's why their iteration time is less, and therefore it's the turnaround time is low. It is best suitable for people who are quickly trying to validate their design or kind of a proof of concept study. And for all the participants, MEMSCAP and Europractice, they ensures that each participant gets a handful amount of die for their design validation, testing, and characterization. So now there are three processes, MUMPS processes, that are offered by Europractice, offered via Europractice from MEMSCAP. They are called SOI MUMPs, Piezo MUMPs, and PolyMUMPs. SOI MUMPs is a silicon-on-insulator bulk micromachining process, whereas Piezo MUMPs is also a silicon-on-insulator bulk micromachining process, but with an active piezoelectric layer on top. And the PolyMUMPs is a three-layer polysilicon surface micromachining process. Now, why shall we go for Europractice? Because obviously it is affordable and easy access to prototyping and small volume production services for both academia and industry. There are other services also available from Europractice. That's like MPW services for various technologies, including ASICs, photonics, MEMS, and gallium nitride-based devices. Europractice can also help the users or the participants for advanced packaging, system integration solution, and test services. And why shall we choose MEMSCAP? Because it's a very cost-effective solution with a very quick turnaround time. The processes are highly standardized. All the processes, SOI MUMPs, Piezo MUMPs, and PolyMUMPs, they're highly standardized. And the entire layer-to-layer dynamics and the process parameters are well understood and documented. And therefore, there is very little requirement of design iteration. So you can be ensured that the design the device you design, you end up getting the same design what you have the same device is what you have designed for. So that therefore the lower and fixed cost development. Okay, so now I will go into the first MUMPS process, and this is the most used and widely used, and I would say the simplest process among all the three. So this is called the SOI MUMPs, that is silicon-on-insulator multi-user MEMS process. For all of the participants who wants to participate, I would strongly recommend them to go through the SOI MUMPs design handbook before starting their designs. So how exactly SOI MUMPs process looks like? So SOI MUMPs process starts with silicon-on-insulator wafer. So it's a 4-mask level SOI patterning and etching process. So the silicon-on-insulator in the silicon-on-insulator, you can see there are 3 layers. So the top one, the red in color, that's the device layer or the active layer. So where the designer needs to pattern their device, and the blue one is the substrate layer, which is basically more for anchoring the entire device as the substrate, that acts as the substrate, and the black one is the buried oxide. So in SOI MUMPs process, there are 2 options of silicon thicknesses are available. One is 10 micrometer and another one is 25 micrometer. And whereas the oxide thickness is 1 micron for 10 micron silicon thickness and 2 micron for 25 micron silicon thickness, the handle wafer is always constant. It's the thickness is 400 micron. So the process works this way. The device is actually patterned from top, and the actual device that you design, that will be on the silicon layer, and the device will be released by backside etching of the substrate and followed by the removal of the oxide, the dry edge of the oxide. And the metal layer, which you use it for bond pad or electrical routing or optical mirror surfaces, that is done by a shadow mask metal process. The process flow starts with a SOI wafer, with a backside backside oxide. The first step is to dope the top silicon layer. So you need to, it is initially not highly conductive. So you need to dope it with PSG. So phosphorus doping is done by depositing phosphosilicate glass, followed by high temperature annealing at 1050 degree in inert environment, mostly in argon. And then the first mask, that is the pat metal mask, that comes into picture. So the metal is that is an alloy of chromium gold that is deposited using lift off process. And then the wafer goes into the first level of etching process, which is the SY, for which the mask called SY is used. So in that, the top layer, the actual device is patterned on the silicon layer, and then it comes the backside etching. So for that, when the backside etching is done, you need to actually flip the wafer. So there is a chance that the silicon layer can can be damaged, and that's why a top protective layer is deposited on that, and then it is flipped, and the substrate is patterned, and through DRI, deep reactive ion etching, the substrate is actually etched using the mask called trench. Once that is done, then the process, then you need to release it. So you remove the protection layer, and the oxide layer is also removed by vapor HF. And so the device is almost ready. Only one mask, that is the blanket metal mask, is left. So blanket metal is for those who want to need bigger pad and very reflective surface, like for optical devices. So there is the blank metal mask that is used to develop a shadow mask using silicon, and that shadow mask is bonded to the other SY wafer, processed SY wafer, and then deposition of again chrome gold that is being done. And once that is done, then you remove the shadow mask and your device is ready. So the devices are diced and into individual or singulated into individual small dies and sent out to the participants. So these are few device demonstrators that have been developed and reported in the literature. So just a couple of them, many of other devices are also available. So left side, you can see there are 4 devices. These 4 devices are from Sambuddha University, that is related to optical MEMS. On the right side, you can see there are 2 images, SEM images, of a device which is basically designed and developed, designed by me and developed or fabricated using SOI MUMPs. It was done during my PhD thesis in Indian Institute of Science, and you can see this is an accelerometer and with a displacement amplifying compliant mechanism. So using this SOI MUMPs process, you can actually design and develop different types of sensors, like inertial sensors, micrometers, actuators, electrostatic or thermal, both types, and then resonators. So those designs were, those images, SEM images were really good, isn't it? So to get those devices, a designer must need to follow certain design rules. Now, what are the design rules? Those design rules are certain guidelines for making the mask layout, and these guidelines have evolved through process development. And the reason is to ensure the greatest possibility of successful fabrication. The design rules, that they define the capabilities of the individual process steps, and by capabilities means what is the minimum feature size, maximum feature size in order for each level or each mask layer, minimum spaces for each level, and then overlay accuracies between individual levels. There are some design rules that are mandatory, some are recommended rules. So mandatory rules must be followed, and recommended rules are good to follow. Then if, like for an example, the minimum line width and space constraints are mandatory rules you need to follow. If the designer violates, then it can give you an outcome of missing structures, undersized, oversized, or fused features. So this is a snapshot I kind of try to put in for SOI MUMPs design rule. And as you can see here, there are 4 lithography levels, that is 4 mask levels. And in this particular table, you can see the SOI MUMPs layer names, thicknesses of individual layers, and their lithography level names, and what is the purpose of the lithography level, and some parameters here. And the second table talks about the again the now one more thing I would like to say here, that when you design the mask layout, so mask layout, in the mask layout you have to design all the 4 steps. So all the 4 steps, and they are to be they are to be denominated with some GDS level number or the CIF level name. So these are the CIF level names that are to be used in the while designing the mask layout. And you can see the minimum feature and minimum space that those constraints are given here for individual level. Like for an example, for the SY layer, the minimum feature is 2 micron, minimum space is also 2 micron. That means you cannot get anything below 2 micron space and feature both. But 2 micron and 2 micron feature, there is a star here. So it says that minimum geometry should only be used when absolutely necessary, and if the geometries are orthogonal in nature. So if they are non-orthogonal structures, then you should keep 3 micron as the minimum feature and minimum space. And then there is something called like maximum pattern area. I'm coming to my next slide that is defined here. So each SOI MUMPs device or die, the size of the die is 11.15 mm by 11.15 mm. So almost like 1 centimeter chip. Now, a designer cannot use the entire area for designing. You need to leave some space around. So the allowable drawing area is 9 mm by 9 mm. And it is suggested that all your critical features, like critical features means that the smaller features, those were very crucial for your device performance, those are to be within 8.5 mm by 8.5 mm area. Now, you cannot, there is something like the SY cannot be etched. There are some certain guidelines that SY in the total mask, you cannot etch silicon more than 33% of the chip area. You cannot etch trench more than 20% of the chip area. And as well as for the blanket metal, you cannot do it, cannot etch the silicon for the shadow mask more than 20% of the chip area. There are certain design, some level to level overlay design rules. Overlay means, you know, like as I already mentioned, that the top layer of the top layer, that is SOI mask, is patterned from the top side of the wafer. Now, for the trench, it is patterned by flipping the wafer. That means from the bottom the alignment is done. Now there could be a possibility that there is an alignment tolerance or misalignment exists between the 2 layers. So that therefore, the MEMSCAP has said that a designer must keep in mind that this the outcome can be of this level, that pad metal to SY there could be a tolerance of plus minus 3 micron, whereas a blanket metal to SY could be of the order of 35 micron. So you have to ensure while designing that if that occurs, your design your design is, or your device is still giving you the required response. So they are basically, they talk about the alignment accuracies here. There are certain pattern constraint, design pattern constraint in all the mask levels. Say for an example, for the blanket metal, you cannot include a donut feature. Similarly, for like while if you want to kind of electrically isolate 2 structures, you need to isolate in this fashion. You need to etch the silicon as well. If you do not do it, if the designer thinks that okay, if I put 2 separate blocks of metal, then they are isolated. They are not, because this is highly conductive or like highly doped silicon. So therefore, they will be shorted. Similarly, again, for trench, you cannot have a donut feature here. So if you have a donut feature, they will actually create a full thickness suspended structure. And in SOI MUMPs, this full thickness suspended structure is not allowed. They, while fabrication they might break, and after fabrication they might break and they might come down. So therefore they don't, SOI MUMPs do not encourage people, or they do not recommend people use full thickness suspended structures. That is not allowed at all. Now there are some more some more design that a designer must follow while designing fragile release structures. Like if a designer wants to design a few beams, and if the beams are anchored at 90 degrees, they are very much prone to prone to breakage because of the inherent stress mostly in this junction. So therefore, a corner filleting is always preferred. So if it is this way, an arc way, then that is the best one. If not, at least a straight line would be good. And without any corner filleting, this is not at all recommended. Again, if you have multiple beams in parallel and they are very close to each other, it is recommended that you incorporate some kind of a dimple here, so that if by any chance, if they come close to each other while releasing or something, they don't stick to each other, because the surface area is reduced and they will not stick if you have a dimple, if you have dimples between the two parallel beams. There are options of chip subdicing. Once the device is processed, you can subdice it. There are two ways of doing it. One is a laser subdicing, one is designed in subdicing. By designed in subdicing means in the mask layout, you have to define the dicing lines, and dicing line all the layers. That means in the trench, you have to define a trench. So you can see the white at the background, that is for the trench. So that is the trench mask. That means that the substrate needs to be removed from this area, as well as from this area and this area. You have to remove the entire substrate from there. And on the top layer, on the silicon layer, there are small beams of 10 micron wide beams. They are to be like, they're the stitching beams. So they will keep them in the same place. Now, once the designer receives those dies, they can actually manually, they can break them, and then they will actually get singulated. But there are some advantages, some disadvantages. I'll not talk about it right now. So laser subdicing has got, definitely it is much easier, because laser subdicing, you need to just define a laser subdicing mark on the SY level, and this is 90 micron. And by the way, here I forgot to mention that from the dicing line, your another say you have a device designed here, and at the same time you have a trench in this place, so that the distance between the from this trench to that is the dicing trench to the design trench, that should be at least there should be a gap of more than 500 micron. Similarly, for laser subdicing, you define the subdicing mark on the silicon layer, and all your metals should be at least 100 micron away from each other, from the dicing mark. So you can, in SOI MUMPs, you can finally get 2 to 4 pieces after subdicing a 10 mm, 11 mm by 11 mm die. There are a few design general tips for layout submission. So layouts, that is the mask layout, must be designed using the technology files that is available, or that are available in Europractice website. Our designer must go through the SOI MUMPs design handbook thoroughly before layout design. In the layout, each individual layer names are to be specified. The layouts are to be converted into CIF or GDS format for submission. If it is CIF format, then CIF level names are to be mentioned. If it is GDS2 format, then GDS level number, GDS number to be mentioned. If a designer misses to include those CIF level names or GDS2 level number, then those levels will be ignored. They will not be fabricated. Therefore, I would strongly suggest that a designer must run a design rule check, that is DRC, on their design on the mask layout. For more details, you may visit the link that is given here. So now I will move into PiezoMUMPs process. Again, I'll strongly recommend the designer to go for the PiezoMUMPs design handbook, go it thoroughly before starting the design. So PiezoMUMPs process is very recent. It has come up very recently, maybe 5-6 years back. And it's a 5 month process, and this is also a silicon-on-insulator based process, where in addition to the silicon-on-insulator processing, a piezoelectric layer is deposited on top of the silicon layer, and thereby you actually end up getting piezoelectric devices. So it starts with silicon-on-insulator wafer, but here the difference between the silicon PiezoMUMPs and the SOI MUMPs, PiezoMUMPs and SOI MUMPs, is that the silicon thickness is available here only for 10 micron, 25 micron option is not here, and the oxide is 1 micron as it was for SOI MUMPs. Handle wafer thickness is 400 micron. The process is almost same, but some differences are there, so I'll talk about it. So it starts with, as I have already mentioned in SOIMUMPs case, so the silicon is doped using PSG deposition, and then the first mask here, the mask called the pad oxide. And in the pad oxide, what happens is that you deposit a thermal oxide, you grow a thermal oxide, thin thermal oxide of 500 nanometer, and then you actually etch the thermal oxide using this pad oxide mask. And once it is, once this the oxide is removed, selectively removed, pattern and selectively removed, then a blanket layer of then piezo film mask is used to deposit the piezoelectric film that is made of aluminum nitride, and it's also 500 nanometer thick. And this is done using a lift-off process. Once the piezoelectric film is deposited, the wafer goes into pad metal deposition. That is also done via lift-off process. Once the pad metal is deposited, you get a connection to your piezoelectric film, and then the first layer of silicon process SY processing starts. So you have a SY mask. So silicon that SY is to pattern the top device layer on the silicon. And then you need to then it is required to actually pattern the trench mask from the backside, and therefore a polyimide layer is is deposited to actually protect the top layer of the piezo film. And then the fifth mask, that is the trench mask, is used to pattern the backside of the wafer, that is the trench using the trench mask to etch the substrate. Once the substrate is patterned and etched, then it is followed by the removal of the oxide by again dry vapor HF process, and then and also before that the protective layer is removed by another dry etching process. So you the designer gets their devices. So here here is the snapshot of the PiezoMUMPs design rule. So you can see here that there are 5 masks that the designer needs to design, and the thicknesses are given here: 200 nanometer, 500 nanometer, 1 micron for the pad metal, and substrate is 400 micron. You can see that CIF level name and GDS level number. Minimum feature sizes are also mentioned here. And here the maximum pattern area is only for SY and for the trench. For the other pad metal and all those maximum pattern area, that constraint is not there. In addition to the SOIMUMPs design rules, there are 2 more concepts that has been incorporated in the PiezoMUMPs design rule. That is called they are called enclose and spacing. So this by enclose, it is defined that one layer is enclosing the other layer by certain amount of by some value. That means here in this figure, what I want to show is that the layer 1, which is in green hashed line, that is enclosing the layer 2 by amount of a micron, and that needs to be kept while defining the mask layout. And then there is a spacing. Two layers will be separated from each other and has to be separated from each other by b micron, say. So for them, there are certain rule letters that has been defined. So SY enclosed paddock. So SY will be enclosing paddock side, and that the reason for them is given here. So SY enclosed paddock side by 3 micron. That means it ensures that the paddock side doesn't cross the SY edge area. So I'll show you here is that for if I go here, see your SY the the pad oxide will be the end of the edge of the pad oxide will be 3 micron away from the edge of the silicon layer. Similarly, there are few more rule letters are given, and their corresponding values are also given here. But you can see here, two of them are in red in color. So that is F and I. They are mandatory to be followed, and the rest are recommended rules that are to be followed by the designer. These are the design rules that are almost same as SOI MUMPs, that is level to level overlay, electrical isolation routing, anchoring fragile structures, chip subdicing rules, and usable area rule. Almost same as SOI MUMPs. There is a great difference between SOI MUMPs and PolyMUMPs in terms of allowed structural constraint. For SOI MUMPs, as I already mentioned, that the thick structures are thick structures are not allowed, but for Piezo MUMPs, the suspended thick structures are allowed if the minimum trench feature is 200 micron, and minimum substrate, that is the mass size is 1 mm by 1 mm and less. These are a few devices, device demonstrator that have been reported in the literature. So here you can see in my left side, there is a piezoelectric resonant gas sensor for detection of benzene gas in the environment. They use PiezoMUMPs process for this, and then another one is a bio-inspired or biomimetic MEMS microphone that was designed and developed using PiezoMUMPs process. And there is another one is a piezoelectric MEMS resonant accelerometer. So there are many more. I tried to give at least 3 of them different applications. There are many different types of devices that you can actually design using PiezoMUMPs process, starting from energy harvesters, ultrasonic transducers, microphones, actuators, resonators, etc. So I completed 2 of the bulk micromachining process. Now I'll move towards PolyMUMPs process, which is a surface micromachining process. Again, I would strongly recommend the user to go through the PolyMUMPs design handbook thoroughly before starting the design. This is 3-layer. PolyMUMPs is a 3-layer polysilicon surface micromachining process from MEMSCAP, and this process is among those 3 processes, this is the most extensive process, and it involves a lot of lithography levels, that is 8 lithography levels and 7 physical layers. And out of those 7 physical layers, there are 3 polysilicon layers, 2 oxide layers, 1 metal layer, and 1 nitride layer. Now, the poly 1 and poly 2 poly layers can be used as the mechanical layers. One poly layer, that is poly 0, is used for electrical layer, for making electrical connections and all. And the metal layer is for probing the devices or for packaging, so for bond pads and everything. An electrical conduction layer, they are called, and 1 electrical isolation layer, that is the nitride layer. And this first oxide and second oxide, they are basically sacrificial layer. So this is a 12 mask process. So as you know, 12 mask process means it's a bit complicated process. The process starts with 6-inch N-type silicon wafer. So as you see here, this is a cross section of a device that is designed using PolyMUMPs process. So you can see on my right side, there is a design that is a micro actuator, micro motor that is fabricated using PolyMUMPs process. So there are some stators and there is a rotor part in the middle of it. So you can actually the process looks like here, looks the all the layers, the cross section of the layer is shown here. So as you can see here that here the poly zero is used as the anchor layer or the electrical layer, and then poly 1, this is for the poly 1 is used for the mechanical layer, that is the rotor here, that will be used as the rotor here, that will be suspended. And then this is anchor, central anchor, and then there are two oxide layers. They will be they will be used for releasing the devices, that is the sacrificial layer. So you can see here, after they actually deposit and etch all the layers, all the 12 masks, then they go for the oxide removal or the release of the device. So once the sacrificial oxide layers, that is the first oxide and second oxide, is removed, you can see you can get floating devices, and these are called the dimples here to ensure that those the poly 1 doesn't stick to poly 0, and they can freely move because the surface area is small here. So this is a complicated process. You can see it's like 12 processes. So first the poly 0 deposition, then oxide deposition, oxide patterning for making the dimple. So there is a mask called dimple, and then once the dimple mask is defined, then the first oxide is selectively etched, followed by the poly 1 deposition. Once poly 1 is deposited and etched selectively, then you go for second layer of oxide deposition, then selectively etched the oxide, and then the anchor 2 creation. Once you create the anchor 2, you can actually you can anchor, or you can, that is to actually create or like ensure the poly 2 or the mechanical layers are anchored onto the substrate. So this is the part here. So anchor 2 actually creates that particular option to gives the particular option to anchor or connect the poly 0 to poly 2. So then there is a selective etching of the poly 2 poly 2 layer, and followed by the release of the devices. So there are so this is a kind of snapshot, and you can see here there are so many like 12 mask layers, mask level name with the kind of field type, whether they are dark field or light field mask, and what are their purposes, their GDS level number, minimum feature size, minimum spacing, everything is mentioned here. So it will be very it is a bit complicated, or I would say it's extensive. So it will be difficult to actually give a complete idea on this process, but I would strongly recommend the designer to go through the PolyMUMPs design handbook. So you can see here there is along with enclose and spacing, as it was discussed during PiezoMUMPs process. There are two more rules that come into picture in PolyMUMPs process. So they are cut inside and cut outside. So for some levels to some level, there is a cut inside and cut outside concept is also discussed, and that needs to be maintained here. So poly 0 to all the levels, there will be some minimum features, some enclosed rules, and some spacing rules will be there. So that this particular table gives a kind of concise overview of all the design rules that needs to be followed while designing PolyMUMPs process. So if you want PolyMUMPs more details on the PolyMUMPs process design rule beyond the design beyond, there are something that is beyond, that comes beyond design rules, that is like recommended rules that are better to be followed, or recommended. It is always recommended that you a designer follow this. There are certain risks, and there are some layout requirements, additional layout requirements for them. To understand them thoroughly, please go through the PolyMUMPs design handbook. You can actually kind of design or develop different types of devices using PolyMUMPs process, starting from acoustic devices, resonators, accelerometers, gyroscopes, microfluidic devices, micro-robotic devices, and display devices, and many more. So you can see I tried to kind of give you a different type of device that has been designed and developed using SOI the PolyMUMPs process, and it's a woven capacitor, and it has been reported in a journal paper. So you can see they using the process, they could actually come up with a stack of capacitor. So it's a woven capacitor with some micron gap size, so you can get a very high capacitance value. So this is done using PolyMUMPs process and reported in literature. So this is the summary of my talk today. So I tried to give you a PolyMUMPs process overview, the SOI MUMPs process overview, and the PiezoMUMPs process overview, and all the design rules that designer must follow while designing the mask layout for the PolyMUMPs, SOI MUMPs, and PiezoMUMPs, all the MUMPs processes. I would like to give a summary of the different like specifications of the dies. So for PolyMUMPs, the die size is 10 mm by 10 mm, whereas for SY and PiezoMUMPs, it's 11.15 mm by 11.15 mm. And then activate design area is 9.8 millimeter square. Here it is 9 millimeter by 9 millimeter. The dies that are delivered to the participants is 15 in number. So each participant gets their design, 15 dies of their design. So in addition to this, in PolyMUMPs process, there is there are some post-processing is available. That is whether you can opt for either released dies. That means there those first oxide and the second oxide will be removed. So the sacrificial oxide will be removed using our HF release and CO2 dry process. So that is critical point drying technique. So it will be the devices will be released and sent it to you, or you can opt for without released devices as well. Subdicing is possible for all the three MUMPs processes. So there are 5 partners in Europractice. That is IMEC, CMP, Fraunhofer, UKRI, and Tyndall. And via Europractice, you can access the MUMP services from MEMSCAP. There is MUMP service or MUMP service from that is offered by XFAB as well, which will be talked in the next session by Dr. Romano Hoffman on April 21st on XMB10. That is the process from XFAB. And there is the last talk of this series by Dr. Vedha Sandeep Nagaraja on May 5th, where she will be talking about the future offering from Tyndall National Institute for people to participate, people to access. So this is the snapshot of the screenshot of the website. So you can actually go into Europractice website through this link given here, and then you can choose MEMSCAP or XFAB or CMP IMEC. And once you go into MEMSCAP for this particular processes, for MUMPs processes, you have to go into MEMSCAP, and then once you go, you get all this, and there you follow the guidelines are given there, and if you fill up certain forms, then you can get in touch with Europractice, and they will help you to actually go forward with your design. I am thankful for to Europractice to give me the opportunity to present present on mumps in this platform. And I would like to thank my team members from PiezoMUMPs group in Tyndall for their support. And also I would like to thank Dr. Veda Sandeep Nagaraja for hosting the session, and Dr. Ramse Salim and Dr. Georges Fagas for giving me the opportunity to talk in this